All right, so this section is on partial derivatives and how to take derivatives in Calc 3 when we've got all these different variables. When we had variables before, we did derivatives called implicit derivatives, and if you can remember, that's when you leave behind like dy dx or dA dt, dB dt, stuff like that. Partial derivatives, though, are when you only treat one variable as a variable and all the other letters you treat as constants. So, if z equals f of xy, then the first partials with respect to x and y respectively are f sub x of xy equals does z to x, yes, those are pronounced does z to x equals the limit of f of x plus h comma y minus f of xy all over h. In other words, x is treated as a variable, y is treated as a constant. And f sub y is where you treat y as the variable and x as the constant. Really what that means is the partial derivative with respect to x, treat y as a constant. This guy down here, the partial derivative of f with respect to y, treat x as a constant. So, let's say I have f of xy equals xy squared plus 3ln x 2x plus y minus 6x squared plus 2y. So I've got this whole thing here. I want to take the partial derivative. Let's take f sub x. So f sub x of xy. Xy squared is really treated as like 3x. The y squared is kind of like a coefficient. So the derivative of xy squared with respect to x is just y squared. 3ln 2xy. Now, there's a bunch of things you could do here with log laws and such, but I'm going to leave it as it stands. The derivative here, the 3 is going to stay, and the derivative of an ln is the derivative of the end over the end, and the derivative of 2xy with respect to x is just 2y. The derivative of 6x squared is, as it always has been, 12x, and the derivative of 2y with respect to x means treat y as a constant, so 2 times a constant is still a constant, and that makes this 0. So f sub x is y squared plus 3y over 2x, no. So this, when I simplify it, is going to be y squared plus, let's see, those will cancel, these will cancel, plus 3 over x minus 12x. Then if I want to do the same thing but with respect to y, I am going to end up with, let's see, xy squared is going to become 2y times x, so 2xy. The derivative here, the 3 is going to stay. I'm going to have the derivative of the end over the end, and the derivative of 2xy with respect to y is just 2x. Again, we're treating the 2x like a coefficient. And then 6x squared is really a constant, and the derivative of 2y is 2, making this in its most simplified form. Let's see, cancel, cancel. 2xy plus 3 over y plus 2. And that is partial derivatives. You treat the variable that's the subscript as a variable, and the one that's not a subscript gets treated as a constant. Now notice I didn't do any product rules. Normally when you did implicit differentiation, that would be a product rule, but it's not a product rule this time because x is a constant and y is a variable, or vice versa. So here's one in z equals form. Z equals all that stuff. Find does z to x and does z to y. It's really fun for the does. I like that. So does z to x, does z to y, and evaluate it at 1 ln 2. All right, fine. So does z to x is the derivative with respect to x. Now this is x times e to the x, so this time I do need a product rule because it's 2x's multiplied. So I have the first times the derivative of the second. The derivative of an exponential is itself times the derivative of the exponent plus the second times the derivative of the first. So this is going to be really e to the x squared y times 2x squared y plus 1. And does z to y is, let's see, I don't need a product rule this time, so the derivative of an exponential is itself times the derivative of the exponent with respect to y, which is going to be x squared. So this is really x cubed e to the x squared y. And now we're supposed to evaluate that at 1 ln 2. So, whoops, pardon me. So this guy at 1 ln 2 is going to be e to the ln 2 times 2 ln 2 plus 1, which is really 2, 4 ln 2 plus 2. And same thing here, 1 ln 2. I'm going to plug the 1 in for x and the ln 2 here for y. And I get 1 times e to the ln 2, which is 2. What in heaven's name does this mean? What have we been doing with that? Well, what this is it's the rate of change of z with respect to x or y individually. It's the rate of change of z with respect to x or y individually. All right, well, what does that even mean? Well, that means if I let y stay the same, so if I look at this point right here, if I look at this graph and I stand on this point and I find a z to x, that means if x goes up by 1, but y stays ln 2, what's the rate of change of z? What do I expect z to go up by? And this is, if I let y be ln 2 and increase and x be 1 and stay the same, what's the rate of change of z? It's 2. Now, this is a picture out of your book that I want to talk about here. So on this one, I'm going to take this photo. I wonder if I can copy it and put it in here. We're about to find out. So if I want to take this photo, beautiful. If I want to take this photo right here, which again I know is blurry and I'm sorry about that, and I want to talk about the derivative, here's what that really means. So if I were to take this and I were to go to the point 4, 1, so 4, 1 is 1, 2, 3, 4, up 1, it's right here. So if you can kind of picture this graph and think about it in three-dimensional form, if I'm at 4, 1 and I want f sub x at 4, 1, that means if x is allowed to increase and y stays the same, what's happening to z? Well, if you think about this, you can kind of see it sloping downwards, so this guy is kind of going to go like that. So if I stay along the same y value but increase my x value, it looks like my z's are decreasing. So f sub x at 4, 1 would have a negative value on this graph because the z to x is going to be negative, z is decreasing. If I stay at 4, 1 and I look at f sub y at 4, 1, that means let x stay the same and let y increase, so move to the right. If I look at that, it looks like the z is increasing, so that's going to be positive. And then this is at the point -1, -2, so let me grab a different color here. Let's do green. If I'm at -1 on x, no, pardon me, -1 on x is back here, and -2 on y is over here. There's that point, -1, -2. And I think about f sub x and f sub y. Let's see, f sub x means let x increase and let y stay the same. That's going to be negative. To z to x would be negative. To z to y, on the other hand, if y is allowed to increase, it looks like z is increasing just a little bit. And that's what this is all about. It's if you change the x or the y independently and let the other one stay the same, what is happening to z? So if I come back to the notes here, you don't have to just take one derivative, just like in Calc 2 and Calc BC, whatever you took last year. You would have the first derivative, and then you'd have the second derivative. Well, you have second derivatives here too, except that there's more of them. So these are called higher order partials. They're called second partials. So I can take the derivative with respect to x twice. That's f sub x, x. I can take the derivative with respect to y twice, f sub y, y. Well, what if I started with x and then wanted to switch to y? That's okay. It's called f of xy. And f sub yx, same thing, except start with y and then take the derivative with respect to x. Here are other notations you're going to see. I just wanted to give you a heads up. So d2z, well, pardon me, duh2z and duh-x with a 2 here. That's the second derivative with respect to x and y. The tricksy ones down here, when you have mixed partials in this fractional form, they're actually in reversed order because you've done duh-x first and then you take duh-y, so it goes to the left. It's just a quirk there. So let's just do a couple and then I'm done. So find all 4 second partials. Well, the thing is I can't find second partials until I take the first partial. So I'm going to go through and do that. I'm going to try to not belabor every step of the way here. I really want purple. Where'd my purple go? I don't know. So we'll go here. And if I take f sub x of sine xy, it's going to be a chain rule. Derivative of the outside, keep the inside, times the derivative of the inside. 3xy squared is going to become 3y squared. 2x cubed y is going to become 6x squared y. There's f sub x. And then f sub y is going to be same idea here, cosine xy times x. 3xy squared is going to become 6xy, and negative 2x cubed y minus 2x cubed. So there's my first partials. Now I do the second one. So what's f sub x? Well, let's see. Fortunately, not a product rule here, yay. So I'm going to have the derivative of the outside, keep the inside, the y would still be there, and then take the derivative of the inside again, so another y hops out. 3y squared becomes 0, and this becomes 12xy. And then let's see, f sub y. Same idea here, not a product rule, but I do have to remember my negative. Sine xy times x again for the chain rule. 6xy when taking a derivative would be 6x. And then this guy goes to 0. All right, now f sub x and then y means start back up here and now take the derivative with respect to y. Oh man, I got a product rule. That's okay. So the product rule, I've got the first times the derivative of the second with respect to y, which is a 1, plus the second times the derivative of the first with respect to y, which is going to be a negative sine xy times x. Derivative of 3y squared is going to be 6y, 6x squared here. So this is going to be cosine xy minus xy sine xy plus 6y minus 6x squared. If I do f sub yx, I'm going to take the derivative with respect to x now. Oh man, another product rule. So I've got the first times the derivative of the second plus the second times the derivative of the first with respect to x now. So y is going to hop back. Derivative of 6xy with respect to x is 6y. The derivative of negative 2x cubed with respect to x is minus 6x squared. So I have cosine xy minus xy sine xy plus 6y minus 6x squared. Wait a minute, I've got a little deja vu here. Well, the nice thing is mixed partials, when you have an x and a y, they're going to be equal. Barring any natural disaster of some weird non-differentiable function, or if you had a jump somewhere, assuming it is differentiable, it's a nice, smooth, run-of-the-mill kind of multivariable function, the mixed partials will be equal. So if fxy and fyx are continuous on an open disk R, that means basically there's no holes or anything, then for every xy in R, f sub xy equals f sub yx. In other words, the mixed partials are equal. Alright, so video done on partial derivatives. Jokes for today. We've got horse jokes today. Why was the pony whispering? Why was the pony whispering? Because he was a little horse. Get it? It's punny, and it's kind of funny. And what do you call it when there is a horse in your dreams at night? A nightmare. Another punny horse joke. Gotta love it. All right. I hope you've loved this. It's fantastic. 14 minutes of partial derivatives, and you get to learn about duh, and I'm done. Bye.